SwayamPrabha. Digital India. Educated India.
Hello everyone. Now we will continue with the drawframe part. In last sections we have discussed the drafting force, ideal drafting process and draft distribution, and now our present topic is nipping of sliver by rollers. So, in drawframe or any roller drafting system, the slivers are drafted through the rollers, where this is a thick sliver and these are drafted thick sliver, number of slivers are thick, mass of material is there, and then this is stretched by a series of rollers. Okay. Now, the main issue here is that these are the say front roller, middle roller, back roller, and these are the bottom rollers, and these two are the back rollers. So, B2 is the top back roller, M2 is the top middle roller, and F2 is the top front roller. Now, the main drive through the gearing arrangement is given to all the bottom rollers, okay. And the bottom rollers drive through the with the help of frictional contact, it gives drive to the top roller. Top roller does not have any positive drive, it gets drive from the bottom roller through frictional contact, and in between the fiber mass is there. So, the friction between the fiber and bottom roller and friction between fiber and top roller is extremely important, and in that along with that the pressure applied by the top roller on the bottom roller through the material is also important. So, without proper nipping the drafting will not take place. So, ideally there should not be any roller slip, the surface speed of the top roller must be equal to the surface speed of bottom roller. So, that we will discuss. First we will discuss the nipping process, then the issues related to the roller slip we will be discussing. Now, if we see the diagram, to move the sliver by pair of rollers. So, these are the pair of rollers. So, first pair, second pair, third pair. The sliver has to be gripped by the rollers. So, this sliver, if they do not gripped by the rollers properly, then there will not be any draft, any stretch will not be there. So, simply the roller will slip. So, our main idea here to stretch the fiber. Okay. This is front zone and here is the back zone. Now, the enlarged view of this nip point is shown here. This is the enlarged view and this is the nip point. Now, try to see the force acting on the in the nipping zone. So, unless it is gripped properly, the motion from the bottom roller will not be transmitted to the sliver, and from the sliver it will not be transmitted to the top roller. That means, the both sliver and the top roller gets motion from the bottom roller and through the at the nipping point through contact. Okay. Now, the rotation of both top and bottom rollers will cause the sliver to move forward. Now, if top roller does not rotate, only bottom roller rotates, then the sliver will not move forward. So, we have to actually move the sliver forward and at the speed of the roller, that is the ideal case. Now, let W equal to force on top roller. So, force on top roller is W, and one component, and here the contact angle is alpha. Contact angle is alpha. So, the arc AC is the contact area. So, contact length is arc AC. So, this load W acting vertically downward, and alpha is the nip angle. So, angle of contact, this is the nip angle. So, here it is a nip angle. Now, at point O, that is the center of the top roller, W can be resolved. So, here the W force is actually resolved. So, here to radial component. So, what is the radial component? This force here WR is nothing but W cos alpha. So, this is the WR, this WR, this radial component which is acting at point A is W cos alpha, and here in this direction W sin alpha, which will not be taken into consideration now. So, W cos alpha. Now, at point A, so from that arc AC represent the contact between sliver and the top roller, that we have discussed. This is the contact. Now, at point A, the frictional force F, this is the frictional force F acts tangentially. So, when the material, this roller rotates, the sliver is actually pushed by the frictional force. So, and it acts tangentially on the sliver, and frictional force F tries to pull the sliver. So, this is actually whatever, this is pulling the sliver from the back, and then it is pushing it to the forward. Okay. And its magnitude, if we see, its magnitude will be mu WR. So, WR is the force acting vertically. So, that is it is a normal force WR, and the frictional force F will be mu WR. Mu is the coefficient of friction, and WR we have already seen, WR is W cos alpha. So, F can further be resolved into two components. This F has got two components, one is F sin alpha and here it is a F cos alpha. So, this one is alpha. If we from the geometry we can see this is alpha. So, F cos alpha, the one acts vertically downward F sin alpha and the other acts along the delivery direction. So, this is acting at the towards the delivery direction, and WR also can also be further resolved into two components, one acting vertically WR. So, that is WR cos alpha, this is that is here WR we are again resolving again two components are there. So, WR cos alpha vertically downward and another acting opposite to the delivery side WR sin alpha. So, WR cos alpha it is in this direction, okay, and here it is a alpha. So, WR cos alpha is acting downward and WR sin alpha acting opposite to the delivery direction. So, here WR cos alpha is there. Now, hence WR sin alpha, this is sin alpha, therefore, oppose the gripping by the roller. So, that is opposing the gripping because it is actually acting against that. So, the condition to be met by this system for gripping the sliver at point A. So, what is the point A? So, F cos alpha is towards the delivery side and which is opposing this thing, it is a WR sin alpha. So, the horizontal component of friction. So, horizontal component of friction is W F cos alpha, which has to be more than equal to the resistance by WR, which is WR sin alpha. So, that condition has to be met. So, F cos alpha should be more than equal to WR sin alpha. So, in that case what we are getting, in this condition the nipping will be proper. So, from this equation we get F by WR equal to sin alpha by cos alpha, okay, and that is, but F equal to mu WR, we know F equal to mu WR. So, mu will be more than tan alpha. So, here F by WR is mu. So, mu should be more than tan alpha. So, the gripping can be improved. So, here what we have to see, this alpha we have to maintain in such a fashion, and mu of the fiber we have to maintain in such a fashion, mu should be more than equal to tan alpha. So, the gripping can be improved by increasing the effective value of mu. So, either mu we can increase here, we can increase the mu value, so that this condition remains valid, okay, and using larger diameter roller to reduce the nip angle. So, what we have to do? We have to reduce the nip angle, so that tan alpha reduces. So, what our idea is that the mu, either mu has to be increased, that is the frictional coefficient we can increase. So, the surface should not be that much polished. So, mu is increased, or we can do the reduce the tan alpha. Reduce tan alpha we can do only by reducing the alpha, this contact angle. So, if we see, if we use the smaller roller, diameter roller, so I will just try to show. So, this is sliver. Now, what we are, if we are using smaller roller, then the sliver thickness is same. So, we will see the angle, this is alpha 1, and if we use for the same sliver, if we use larger roller, very large roller, in that case we will see the alpha 2. So, alpha 2 will be less than alpha 1. So, for smaller diameter top roller, the alpha will be much more than when we use the larger diameter top roller. So, if we use the larger roller, so in that case alpha will be reduced. So, tan alpha will be reduced. So, we can have this equation will be satisfied. Okay. Now, we can see here in this diagram. So, one is the larger diameter and here is a smaller diameter. We can see the alpha, if we are using alpha for both the cases. So, for larger diameter roller it is alpha contact angle, but when we use the smaller diameter roller, the additional, so alpha plus delta alpha, the additional contact angle will be there. So, that is the reason. So, we always actually try to use the larger diameter roller at the top to reduce the to have better contact and to reduce the slippage, proper contact. So, with a smaller roller, the nip angle alpha increases, therefore, gripping reduces. So, we have to increase the gripping. Now, our next topic is the roller eccentricity. So, roller eccentricity is again very important aspect. So, this generates a fault due to roller eccentricity, we get the periodic fault. Okay. So, roller eccentricity generates the periodic fault, that is actually that ultimately it cannot be eliminated at the even at the ion stage, and the fabric appearance will be poor. And this roller eccentricity, the defective roller, we can identify by using the spectrogram method, that we will discuss subsequently. But first let us see what are the implications of roller eccentricity, and we will do some theoretical calculation. So, if you see the in the figure, this is the figure A and this one is the figure 2. In these two figures, so the bottom roller, it is considered the bottom rollers are eccentric. Okay. These are the eccentric roller. In this condition, this one is the O is the center, effective center of the roller. So, this has become eccentric. So, one side, the top side, its diameter is radius is more, and here its radius is 2. So, the level of eccentricity, it's E. Here this is called positive eccentricity, and here it is a negative eccentricity, where the effective radius is low. The shaft position, that is center, shaft position of the bottom roller is O. This is at this position, this is the shaft. So, this is the shaft position. Okay. So, O is the shaft position. Now, the roller diameter are dr for both the rollers, the roller diameters are dr, and the extent of eccentricity is E, that is off center. For both the cases, epsilon is the extent of eccentricity. The rotational speed of front roller and back roller is assumed to be N1 and N2 RPM. Okay. So, N1 and N2, these are the rotational speed. Now, let us see velocity of the input rollers. So, this is the velocity of the input rollers are the V in roller. So, dr is the diameter, effective diameter of rollers. So, all the rollers with have dr. So, pi d n. So, 2 pi n by d by 2 r. So, this is actually pi dr n 2. So, velocity of feed roller or input roller for both the cases, we can get pi dr into, this is the velocity, here also pi dr into, this is the velocity, actual velocity here. Now, but in case of front roller which is eccentric, the velocity will not be equal to pi dr n1, it actually it will vary due to the eccentricity. Now, at position A, when the diameter effective radius is more, so what is the effective radius? dr by 2 is the average diameter radius, and dr by 2 is the average radius plus epsilon. This is the effective radius. So, effective radius is this much. Here it is a dr by 2 plus epsilon, that is effective radius. So, the velocity, the at the bottom of the bottom roller at point A, at this will be 2 pi n1 multiplied by dr by 2 epsilon. Similarly, the velocity of bottom roller will be in this case in at point position B, it will be 2 pi n 1 dr by 2 minus epsilon, because here effective radius is dr by 2 minus epsilon. So, this is the velocity. And now, if we see here, so from the roller contact point, so nip point, so what we have observed that this velocity will be actually transmitted to the top roller through the contact of the sliver, and the sliver will be pulled at point B with this speed. Okay. And so, VB out means delivery roller. Similarly, at point A it will be pulled by 2 pi n 1 multiplied by dr by 2 epsilon. So, we can see this is moving at higher speed and this one is moving at lower speed. So, at this point, at point A, there will be maximum stretch, because the back roller is moving at constant speed, but at point position A, this position there will be maximum draft. So, what will be the draft? This V A out by V A in, V A in is constant. So, this is the maximum draft. Similarly, minimum draft will be V B out by V A in. So, V B in, V A B in or V A in are same, because there is no deviation in diameter. Therefore, the speed of the emerging sliver will vary for each rotation. So, whatever sliver is emerging, that will vary. Point A, the speed will be high with the higher draft, and here it will be lowest with the lowest draft. So, as it is highest draft point A, so there will be stretch, maximum stretch, this will result thinner sliver, thinner output, and here as the draft is low, so it will result the thicker sliver. So, the draft in these two positions will be position A. So, V A out by V in. So, V A out is 2 pi n 1 multiplied by dr by 2 plus epsilon, and V A in 2 pi n 2 multiplied by dr by 2. So, just simplifying this equation, it is n 1 by n 2 multiplied by 1 plus 2 epsilon dr, that is the draft in this position A, and draft in position B, it will be simply 1 minus 2 epsilon by dr. So, we can see the draft in position B is much less than, much lower than the draft in position A, and it depends on the level of eccentricity, that is the deviation from that point. So, the length of sliver delivered per revolution by the bottom rollers pi dr, okay, that is the length of sliver delivered per revolution. So, draft will vary, okay, cyclically. So, when the position A reaches, the draft will be maximum, and when the position B reaches, draft will be minimum. So, there will be, as it is rotating, there will be cyclic variation of draft, and it will introduce a drafting wave. The wavelength of that drafting wave will be pi dr, okay, because the effective length fed per, so average length, total length delivered per revolution of the bottom roller will be pi dr. So, it will vary from this length to this length. So, the percentage error will be, this is the percentage error. So, at one place it will be plus 2 epsilon by dr, and other place it will be minus 2 epsilon by dr. So, percentage error will be plus minus 2 epsilon by. So, in one place will be plus epsilon by dr, and in other case minus epsilon by dr. So, that we have already seen in earlier case. So, 2 epsilon so plus minus 2 epsilon by dr, okay. And that is the percentage error if the back bottom roller is eccentric. Now, what we have discussed, this is the eccentricity of the front bottom roller. Now, if the back bottom roller is eccentric, then what will happen, the same thing error will be there, same variability or will be there, same calculation will be there, but only thing is that this here if it is a draft, D is the draft, then it will be multiplied by the draft. So, it will be stretched by that part, and if the both the rollers are eccentric, then there will be superimposition. So, there will be multiple wave will be there. So, the wavelength variation is pi dr z, where z is the draft, here that is the z, here it is kept the z as draft in this zone. So, pi dr multiplied by z, that will be the wavelength. So, if the top rollers are eccentric, so this is the bottom roller, this is eccentric, but if top rollers are eccentric, what will happen? Because as we know, the top rollers are not driven positively, they move by the contact point with the frictional contact from bottom roller. So, that is why they will, whatever motion they will actually generate, whatever they will, their surface speed will be same, because as the bottom rollers are perfect. So, their surface speed will be will remain same, that is why no error will be produced, as the top roller surface speed does not change, because bottom roller is not changing from at different point. But if bottom roller, as we know that if the bottom roller is eccentric, so at different position of the roller, the speed of the bottom roller changes, and accordingly speed of the top roller changes. So, draft changes. So, if the top roller is eccentric, so there is no such effect. So, that is why what happened? So, top roller is normally we use as the rubber coated, rubber or synthetic coating. We get multiple advantages. One thing is that in rubber coating, rubber like cords, if we use rubber covering, there is a chance of eccentricity because of the pressure and all that, there is a deviation, and that deviation, if it is there in the bottom roller, then we will get the eccentric, that periodic fault. But if there is little deviation or little eccentricity in the top roller, so it does not affect the material characteristics. And another thing we achieve by using the top roller as this synthetic coating, rubber coating, it gives higher frictional contact. So, higher frictional contact is required for better transmission of motion from bottom roller to top roller, and to increase the friction of the bottom roller, we use the groove knurling. So, that is why that is how the friction increases. Okay. Now, so the eccentricity could also be due to improperly mount or poorly made gears. So, that is why improperly, if we mount, so this is the eccentricity, but if we mount the rollers improperly, that also will generate the eccentricity, but the actual calculation will be same. Now, our next session is the roller slip. Okay. Roller slip is extremely important in drawframe blending or any drawframe drafting or any other drafting. So, if suppose this other roller, two sets of roller. Okay. Now, here this is front roller and back roller. Now, this bottom roller, front bottom roller is rotating, and the idea is to pull the fiber at the same speed, pull the fiber strand, and from this fiber strand, through the fiber strand, the top roller also rotates. Top roller should have the exactly same surface speed, but if the surface speed, if there is any slippage here, suppose it is rotating, its surface speed of say V1 is the surface speed and V2 is the surface speed of back roller, then effective draft should be V1 by V2. Okay. Now, if there is any slippage due to any reason, if there is any slippage between the bottom roller and fiber mass, what will happen? So, this V S is the speed of the S1 front roller after the slippage. So, what will happen? V S1 will be, that is, this is the sliver after slippage, due to slippage. So, V S1 will be less than V1. So, roller is rotating, moving at V1 speed, but sliver due to slippage, sliver is getting lesser speed. So, in that case the draft will get disturbed. So, there are two types of slippage, one is forward slippage and backward slippage. They are related with the drafting force, that let us discuss this issue. In the draw frame, the bottom rollers are driven directly by set of gears, is positively driven, which in turn connected to the motor. So, through motor, through gear, bottom rollers are driven directly positively. So, there cannot be any slip, because gear does not slip. If there is a belt pulley, then there can be slip at the back one, but at the in case of the gear system, so there cannot be any slip. Okay. So, then what happened? The top rollers are driven by the bottom rollers through the frictional contact. So, there will be frictional contact. So, through the fiber mass. Now, here again the similar diagram is there. So, this is bottom roller, here is the top roller, and through this fiber mass the top roller gets drive, and here the frictional contact is there. While running, there is no direct contact between the top roller and bottom roller, because in between there is a fibers. So, fiber mats are there. So, thick fiber mat stays between them. So, this is no direct contact. So, in between the rollers there is a thick fiber mat is present. Now, the bottom roller drives the fiber on it. So, this bottom roller will first drive the fiber on it, and the fibers then in turn drives the top roller. So, the top roller gets drive from the bottom roller through the fiber mass. So, it is a thick fiber mass. In case of sliver or in Drawframe, it is very thick. Only top rollers have the possibility to slip. Bottom roller cannot slip. Bottom roller will move at its speed. Only the top roller has the possibility to slip. So, the draft will change. So, because it is a negatively driven. So, the slippage means that the speed at the top roller is different from that of corresponding bottom roller. So, the slippage, top roller is bottom roller is rotating at speed, certain speed, okay, and then top roller rotates at different speed. Now, if you see the middle roller, middle top roller can rotate higher than bottom roller speed, middle bottom roller speed. So, that depends on the whether the slip is forward slip or backward slip. So, this issue we will discuss here. So, ideally the speed of the top roller and bottom roller should be same, and the reason for slip is the imbalance in drafting force, okay, in the consecutive drafting zone. So, there is a drafting force in between the zones, and if the drafting forces are imbalanced, okay, then the slippage will take place. Now, let us see the things here. At the back zone, the number of fibers are thick fibers are there, it is compact, and at the front zone number of fibers are lower, because the back zone draft is there. Now, what happens here, as we know, the drafting force depends on the number of fibers, okay, and here the drafting force, if we consider the nip lengths are same, the drafting force at the back zone will be higher than the front zone. Now, as it is higher than the front, so front zone, the front roller is pulling the fiber strand, it is moving, but at the back zone, due to higher drafting force here, this actually drafting force, and this is back roller is moving at slower speed. So, that is why what happened, this the sliver strand at back roller, fiber strand at the back zone tries to pull the roller back, it will give a the force in the opposite side. So, which will actually result the slowing down of the middle top roller as compared to the middle bottom roller. So, that is called, it is a negative slip. So, here the imbalance of drafting force is actually main reason, consecutive section. So, if the drafting force in all these sections are same, then we will not have this type of problem. And how these types of situation are eliminated. So, I will discuss in detail, but in general term what we do in back zone we use the higher setting, longer setting. Main idea here is to reduce the drafting force as we change the setting. So, if we keep the larger setting at the back zone, so here the number of fibers are more. So, it will obviously give higher drafting force, but if we increase that setting here, so when there is a slippage takes place, you increase the back zone setting, that will be that will actually balance the drafting force. So, imbalance of drafting force is actually the reason of the backward slip or any slip. Okay. So, drafting force has to be balanced. It depends on the grip of the roller also. If the grip of the roller is less, then there will be slippage. So, that means the top roller pressure is important, and also the friction between fiber mass and the roller is also important. So, the grip of the rollers in relation to the force required to draft the sliver in two zones. So, in addition to the drafting force, force required to draft means drafting force, the frictional contact or grip of the roller is also important. So, basic thing is that for to actually control the roller slip, we have to take into account of the grip of the roller and also the drafting force. These two aspects we have to take into account. So, the drafting force is inversely proportional to the draft also. So, another thing we have discussed earlier when we derived the drafting force. So, drafting force is inversely proportional to the draft, whatever draft we are giving in the fiber strand when the draft is above the stick slip region. So, the roller slip is it also increases rapidly as the setting becomes closer to the fiber length. That means, if the setting is very close, that means drafting force will be very high. Okay. In that case, there will be slippage, and also if the fiber length is more than the setting, it is very low, then also the roller slippage will be there, fiber will start slipping. That issue we have already discussed, and there can be two types of slippage. One is backward slippage, backward slips, and another is forward slip. So, these two issues we will now discuss. The backward slip, the sliver, now this is the backward slip situation, the sliver held back by the roller behind that and causing the top roller to run at slower than the bottom rollers. So, if we consider the second roller, so it is a 4 roller drafting system we are discussing, which is the conventional drafting system was there. So, in 4 roller drafting system in the draw frame, we are considering the roller second roller, and here the draft distribution is that 1.2 at the back and middle zone draft is 1.7, and in front zone we are giving 2.9 draft, and this roller middle roller we are actually considering its slipping is there. What is that? If the middle roller slips, middle top roller, what will happen? V 2t, that means second top roller speed is less than the second bottom roller. So, this roller will rotate move at faster rate than. So, there is a slippage. Now, to enlarge this we are using this diagram. Here it is a second bottom roller and second top roller. Okay. Now, we are now discussing the backward slip, the draft T1. So, the T1 is the drafting force in the front zone acting at the forward force. So, here there is a drafting force, that means this strand will be pulled at force T1. Okay. This is at front zone, and drafting force at the back zone it is T2. T2 is the drafting which actually resists the movement of the second top roller. F1 is the friction on bottom roller. So, F1 is the friction on bottom roller, frictional force, that is frictional force between the bottom roller and bottom surface of the fiber mass. As we, this is bottom surface, this is the frictional force, okay, which actually acts, which is used to pull the fiber forward, and F2 is the reaction force. Okay. F2 is the reaction friction force which is required to slow down the top roller acting backward. So, due to this, it is this reaction force is acting at the backward direction. The draft distribution is such that the number of fibers under the front roller nip is about say 1/3 of that of middle roller nip, because draft distribution it is approximately 2.9. So, here if the draft is 3 here, so number of fibers at the front roller nip will be about 1.1/3. It is basically 1 by 2.9 as per this picture. So, this is approximately 1/3 to that of middle roller. So, as the number of fibers is less here at the front roller, so drafting force will be less. So, as a result the drafting force T1 will be much lower than T2, that so T1 will be lower than T2. Hence, the second top roller is prone to slip. So, this the T2 will be pulled, it will actually resist the movement of the top roller, second top roller. And now, the condition for slip is that T1 plus F1 is less than T2 plus F2. So, at the backward force, total backward force should be more than total forward force, forwarding force. So, T1 by F1 is less than T2 by T2 plus F2. So, T2 plus F2 will try to pull back the top roller and it moves slowly. Although they will move in the forward direction, but it will be at the speed of the third roller. Or just rearranging the F1 minus F2 is less than T2 minus T1. So, for no slip condition, so if there, this is the slip condition, slippage. For no slip condition it will be just reverse. So, F1 minus F2 should be more than, so F1 minus F2 should be more than T2 minus T1 for no slip condition, because that will actually the second top roller will move at the speed of the second bottom roller at that condition. So, F1 minus F2 is more than T2 minus T1. Now, various options we have to now see. So, this is the condition here, this is the condition, no slip condition. Now, how to achieve this condition? Now, let us see the main, and accordingly the draw frame development took place. So, the main conditions are, now see, for option F option, in case of if we want to maintain this equation. So, what we have to do? We increase F1. So, what is F1? F1 is nothing but the friction between the bottom roller and the fibers. So, how to increase the friction? To have flutes on the bottom roller, that is why we use the flutes and increase the top roller pressure. So, we increase the top roller pressure. So, to increase F1, F1 is nothing but the frictional contact, and frictional contact, as we know that we have discussed earlier. So, the frictional force, and frictional force is actually the frictional constant and the normal force. So, normal force if we increase, the F1 will increase. This is one way, and another way to reduce the T2. Either we increase the F1 or to reduce the T2. How the T2 will get affected? So, we reduce the T2. Okay. Now, T2 we can get affected to reduce the draft in the middle zone, and it will be close to 1. So, we do not use any draft at the middle zone. So, if we can do it, then drafting force will be lower. So, that is why we will see in the modern system the development was there, is there in the middle zone we keep the draft in this fashion, then it is a front zone. Here the draft is 1. We use single roller top roller over 2 bottom rollers. So, that this forms the middle zone, and it is giving, if you maintain here draft 1 if we want to maintain, otherwise we can simply reduce the draft here, we can reduce the draft. So, at this zone we reduce, at the back zone we always reduce the back draft here. So, in place of 1.7 we can make it 1.1 like this. Have one common top roller, that is what I discussed, on 2 bottom rollers. So, this makes the draft second and third roller 1. So, here in place of 2 rollers we will use 1 roller and in place and 2 bottom rollers. So, this we will do. So, here 1 draft is maintained and increase the setting at the back zone. So, if we increase the setting at the back zone, then also drafting force will reduce. So, T2 will be actually T2 is this T2 will be reduced, decrease the T2. So, we can decrease the T2 in this fashion. Increasing the setting means we are reducing the drafting force. So, this is the way of doing, this is the middle roller, front roller, top roller. So, then that is the reason we do that 3/4 or 3/5, this type of setting we do, because just we want to maintain the draft low at this point. This is the point. Now, the fibers are pulled by the roller ahead. So, any fibers they are pulled by the rollers which are ahead, and what we are now discussing, the forward slip. So, earlier which is very common, the backward slip, now we are discussing the forward slip. These fibers will pull the roller ahead, causing the top roller to run faster than the bottom roller. So, if these rollers are pulling the fiber, and these fibers are pulling these rollers ahead, the top roller ahead, because bottom roller will move at its own speed, because as it is positively driven. But if these rollers are pulling, these fibers are pulling the roller ahead, then there will be forward slip, because the top roller will move at higher speed than the bottom roller. Here you can see that this is the 3T and 3. So, we are discussing here the out of 4/4. So, we are discussing here second, third and fourth rollers. So, V3T top roller is moving at higher speed than V3B, that is the third bottom roller. This is called forward slip. This with the 4/4 drafting system, the conventional draft distribution, the bulk of material in the back zone is more than the middle zone. So, this is the back zone, bulk of material, and here it is a middle zone. So, bulk of material is more, and what happened here, we can see this, if the setting of two zones remain fairly same, the third roller will tend to slip backward. So, this third roller will tend to slip backward, because the forces acting at the back direction. This third one will be, however, the back setting is kept much larger. This back setting is kept much larger to reduce the drafting force. So, we want to keep the drafting force at the back zone, because the number of fibers are more. So, we keep it larger. So, if T1 is more than T2 plus F2 plus F1, because normal case the F2 should act at the backward direction, and this will, and F1 is also moving at the backward direction. It is actually, this is acting, because here the pull is at the front direction. So, in that case T1 minus T2 will be F1 plus F2 from this. So, then the third top roller will slip forward. So, if in this condition T1 minus T2 equal to F1 plus F2. So, if T1 is more, then only the third top roller will try to move faster speed than third bottom roller. So, at this condition, now how this condition is achieved, that we will discuss. The condition is satisfied only when F1 and F2 are too low, because T1 minus T2 is more than F1 plus F2. So, F1 and F2 has to be very low. So, how the frictional force can be very low, frictional resistance, that can be very low when, if the one is the top roller pressure is low. If the top roller pressure is low, then frictional resistance will be low, and if we use very smooth surface, then also frictional resistance will be very low. So, in no slip condition, F1 plus F2 it will be just reversed, T1 minus T2. So, no slip condition, forward slip we are discussing, F1 plus F2 is more than T1 minus T2. So, what are the option? If we want to have no forward slip condition, in that case we can increase both F1 and F2. If we can increase both F1 and F2, and that we achieve that have a flute on the bottom roller. If we have flute on the bottom roller, we can increase F1, and if we have rough surface change here, so that we can increase the friction between top roller and fiber mass. So, F1 and F2 can be increased, and increasing the top roller pressure that I have mentioned earlier, and then decreasing T1 and increasing T2. So, if we decrease the either decrease the T1 and increase the T2, in that case we can achieve. So, what we do to do this thing, reduce the draft in the middle zone and increase the draft at the back zone. So, middle zone draft is reduced and increase the draft at the back zone, so that we can manage this thing, reduce the draft. These are the drafting force, and have one common top roller on two bottom rollers. This makes the draft in third and bottom roller approximately 1. So, that is why what we do, we use the three over 5 arrangement. So, this will help in reducing the forward slip, and as we have discussed, this will help in reducing the backward slip. That way we can manage the roller slip. So, this is the way we do. Now, our last section here in this discussion will be analysis of roller setting. So, roller setting is very critical for the production of good quality sliver. So, roller setting is normally it means the distance between two nip point, and if the roller arrangements are this is the simplest arrangement, then calculating roller setting is not a problem. We simply can calculate the distance between the center of two rollers. So, that is, but in actual practice the rollers are not placed in a single plane. So, rollers are placed at different plane, and at the same time rollers are not positioned just above one. Sometimes the rollers are actually tilted in one direction towards. So, they are not actually just above one thing. So, they are not in same plane, they are shifted either backward or forward depending on the requirement. So, that is we will actually see the how the roller setting is calculated. So, this is the arrangement here. Let us see the two rollers, two pair of rollers. This is back pair and middle pair and front pair, front and middle. Here this setting point, nip point at the middle zone is P and nip point at the front roller is B. So, they are not in the same plane, and at the same time they are not in touch. So, there is a gap between the gap is denoted by A. So, accordingly we will now try to calculate the roller setting here, roller to roller nip to nip distance here at this, as per this picture it is a PB. PB is our idea, but whereas the center to center distance TO, we can see the A is the gap at that point. So, when the rollers are not in the same plane, the sum of their axial distance between the bottom roller and the gauge. So, this bottom roller, this axial distance and the bottom roller is not equal to the nip to nip distance PB. So, this is not the case here. So, it is not the this radius plus A, it is not that straightforward over which the fibers get drafted. So, fibers are getting drafted between these two rollers, this point, okay, P and B. Nip to nip distance governed by that actually the this all this arrangement theta and what is the plane position, and this distance is important and which controls the irregularity of the sliver generated. Let us take the case of 3 roller drafting system, where the front top roller is not placed exactly on the top front roller. So, this is not exactly at the top, it is shifted here, shifted by x towards the front, but slightly ahead of its center by x. The bottom drafting rollers are on different plane, these rollers are of different plane. This is this front roller is in this plane and middle roller is in this plane. They are placed in different plane. The center of center O, the center O of the front bottom roller is at lower level than the center of the middle bottom roller. So, they are at different plane. Let the diameter of the front and bottom middle roller are df and dm, these are the diameters, and A is the gauge thickness. So, between there the roller to roller distance is A. So, we can see here the distance between OT will be df by 2 plus dm by 2 plus A. This is the distance. From the geometry we can see the PS, that is PS, what is this? PS is the diameter of middle roller and PS is nothing but OQ, this OQ, and QR, what is QR? QR is nothing but OQ minus OR. So, OQ minus OR, what is OQ? OQ is dm as we know here, and OR is the radius of the front roller. So, df by 2. So, QR is calculated. Now, from this triangle PQR, so PQR we can calculate the PR by, so this we know this is A, the center to center distance, axial distance, center to center the distance, not axial, the A is the center to center distance in the vertical plane. So, using equation 1, we know the QR equal to dm minus df by 2. So, QR we are replacing. So, PR will be under root PQ. What is PQ? PQ is equal to A. So, A square plus QR square. So, this is now nip to nip distance is, what is the nip to nip distance? This distance and this distance. So, this is the PR is that distance plus the arc RB. This is arc RB, but as it is a very small, this arc RB can be assumed to be equal to x, the distance x. So, arc RB. So, arc RB can be assumed equal to x of the front roller. Okay. So, x is the shift towards the front, and now for triangle OTS. So, OTS in this triangle, what we get? A square equal to OT square minus ST square, and now then the center to center distance A, this is center to center distance A we can calculate. So, OT, what is OT? OT square, OT equal to, as we have already seen, diameter radius of the middle roller plus radius of the back roller plus A. So, radius of middle roller and back roller and plus A, that is the OT, and ST, the ST is equal to, what is ST? So, ST is nothing but the radius of the middle roller. So, dm by 2. So, from there, so the drafted fibers emerged from the delivery roller nip at an angle with which is close to tan theta. So, that is here drafted sliver. So, that is from the delivery point, it is angle with the horizontal plane. Now, from the geometry we see that we have seen the tan theta. What is tan theta? QR by PQ. So, tan theta QR by PQ, QR by PQ, okay, from this geometry. So, QR is dm minus df by 2 and PQ is nothing but A. So, that is tan theta, and therefore, theta, this angle is tan inverse dm minus df by 2 by A, this is tan inverse this. So, that theta angle for a given value of dm, df and A. So, dm, df, A we can, so the dm and df. So, as we increase the setting, we can reduce the theta. So, as we increase the setting, so A is increasing, roller to center distance if we increase, then we can reduce the theta, that means we can reduce the tan theta. So, theta can be reduced here, A is reduced. So, from here we can actually do all these calculations and we can actually calculate the roller setting distance. Now, we will discuss the blending delay time at the draw frame. We have discussed the blending delay time in blow room and how we can control the blending delay time also in carding. Now, here blending delay time in the blow room draw frame section. Now, in draw frame we normally set 6 to 8 slivers are fed parallel to the drafting unit. So, that we feed. If the slivers originate from the same carding machine, then the slivers produced over the period of time get opportunity to be mixed on the draw frame. So, blending delay time means you are actually at different time you are feeding, but they will be they will get chance to be mixed up. Slivers, let us see the slivers from first, second till nth can are brought together for doubling and drafting at the draw frame simultaneously. So, suppose there are n slivers fed at the time in the draw frame, it is typically 6 to 8, n is typically 6 to 8. So, n slivers are there. Now, if it is coming from the same card, okay. Now, carding is a card 1, 2, 3, 4, its cans are produced and they are coming to the different to the same draw frame. So, can 1 is coming at this position, can 2 is coming at this position, can 3, can 4. So, nth can is coming at this position and they are actually mixing together. So, that means they are produced at different time, but they have the chance to mix together. So, here what will be the blending delay time? Blending delay time will be the time to fill one card is T, and from the nth for first after first one the nth card will take time. So, NT. So, that is the NT is the time which is after NT time the same sliver is fed with the which is delivered after T time. So, this is the maximum difference in time. So, in that case the blending delay time is calculated. So, sliver from n plus nth can they have no opportunity to get mixed with the sliver, but nth can will have opportunity to mix there because they will get exhaust at the same time. So, then next cycle will start. Thus, blending delay time in this case is the difference in time required to produce the first and nth sliver can be doubled in the draw frame together. Let the n be the sliver can number of can having a capacity of m kg. So, one can has a capacity of m kg, and if we know the delivery speed and the sliver hank, then we can calculate the total time required per can. So, delivery speed kg per minute. So, delivery this is the in kg per minute and m is the total capacity. So, for fast can the time required is m by m, capital M is the total capacity and delivery rate. So, that much minute is there, and for nth can it will be T n. So, n multiplied by m by m. So, this difference T n minus T 1 is the blending delay time. Blending delay time will be T n minus T 1. So, m by n multiplied by m multiplied by n minus 1. From the above equation, it can be said blending delay time depends on the, if we increase the, this is the delivery, if we reduce the delivery capacity, then blending delay time will be increased. If we increase the can capacity, then blending delay time can be increased. So, number of slivers doubled n. So, if we increase the number of sliver, so for 6 sliver blending delay time will be such, it is lower than if we go for the 8 number of sliver at the draw frame can capacity. So, this can capacity, if we increase the can capacity, blending delay time will be increased and the production rate of card. So, these 3 factors are important for blending delay time in the draw frame. So, we and here the condition is that they are coming from the same card. Okay. Now, however, if the can capacity remains same, the production rate of the can of the card changes in the time required to fill can. So, can capacity is normally remains same. In real sense, the quality of material getting mixed up does not change, the quantity does not change, though the delay time may be reduced. So, that they can be reduced. The weight equivalent of blend delay time is therefore, the total weight of sliver, okay, that can be mixed with the sliver in the first can. So, that is the weight equivalence of blending delay time. So, here this is the equation, weight equivalent of blending delay time is n m minus m, which m equal to m multiplied by n minus 1. And this is the normal blending delay time. So, where we are actually considering m is constant, okay, no change in the can capacity. This is the weight equivalent, where m this material delivery is normalized. I think we have come to the end of this session. In the next session, we will discuss a new topic. Till then, thank you.